Okay. 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 So, previously we talked about this match-Paris algorithm, and we also show you like some arguments why it worked. Okay. But it turns out that we can generalize it. Okay, to make it more applicable to to a lot of cases. Okay, because in previous the partition example, we consider only simple case of discrete positions. Okay, we have like a chain of islands, right? And on one dimension, because it's one-dimensional islands. Okay, the islands are distributed in one dimension. Okay, and with moves that propose just one position left or right, we each time, okay, we flip a coin and decide to propose to move left or right. And then, of course, we need to determine whether or not we really move to that particular island, okay, based on the ratio of the populations, right? So this is the simple case, okay? But it turns out that we can generalize it, okay, in a much more realistic scenario. Okay, it can be used for continuous values on any number of dimensions and with more general proposal distributions. Okay, remember what the proposal distribution means. Okay, the proposal distribution means like where you can propose to move, as well as the probability, okay, distribution for your proposal. Okay, in the previous simple case, the proposal distribution is so simple because you only have like a left or right, two cases, and also each of them is 50% chance because it's a coin flip, right? So, but now, okay, it can be much more complicated. Okay, it can be much more complicated. The proposal, can be drawn from the continuous space, and also the probability doesn't necessarily need to be, the same for each proposal. Okay, so first we have some target distribution. Okay, P of theta, over a multi-dimensional continuous parameter space, from which we would like to generate representative sample values. So now, okay, this situation is much more similar to our posterior distribution case. Okay, because the posterior distribution is a multi-dimensional continuous parameter space. Okay, so we must be able to compute the value of P of theta for any candidate value of theta. Okay, which is not a problem. Okay, if you want the P of theta, I mean not exactly P of theta, but like something that is proportional to P of theta, which is like the likelihood times the prior, right? Okay, the distribution P of theta does not have to be normalized, okay, because we only want something that is proportional to that. Okay, in typical applications, P of theta is the unnormalized posterior distribution on theta. So it's a product of likelihood and the prior, as I already mentioned. Okay, so sample values from the target distribution are generated by taking a random walk through the parameter space. So it's still a random walk, okay? And the walk starts at some arbitrary point, okay, specified by the user, okay? Just like the partition, okay, we can start the position of the partition from island 1, island 2, island 3, island 4 to island 7. It doesn't matter, okay, because it's a random walk. Eventually, the partition will move to move more often to the places, to the islands with more populations. Okay, eventually. Okay, so the starting point should be some place where P of theta is non-zero. Why do we have this constraint? Because remember, okay, no matter what, it's a special case, the simple Metropolis algorithm or the general Metropolis algorithm, okay. At the end, when you decide to accept the proposed move, okay, or not, you are going to end up, checking this, where is it? This value, right? The P move is going to be mean of P theta proposed divided by P theta current, or 1, right? It's a smaller one of these two terms. So if your P theta current is 0, we have an issue, right? We have an issue. So this term, the initial location of this, the P theta of the initial location has to be non-zero, okay? But it's normally not an issue, normally, okay? If it's really going to be an issue, you can certainly start from another initial location again, okay? If you found that, okay, this place, it doesn't lead you to go anywhere, most likely you have this initialization issue. You can change the initial location. That's pretty easy, and you don't need to worry about, once you get a good start, you don't need to worry about that you are going to, go to some place that have with the P theta to be 0. Why? Because if the P theta proposed is 0, you can never go there, right? Because the probability of moving there is going to be, this term is going to be simply 0, right? So you don't need to worry about if you have a good start, whether or not, after you move several steps, it's going to go to a place where the P theta is 0. This is impossible, okay, according to the Metropolis algorithm, okay. This P move is definitely there, okay. Actually, it's this P move, okay, that's guaranteed the result is going to converge to the target distribution. Okay, you can see that the proposal distribution, okay, what the proposal distribution impact is how quickly the sampling process converge to target distribution, but it doesn't really create a problem of the conversion, okay? So come back to, so this random walk progresses at each time step by proposing a move to a new position in parameter space and then deciding whether or not to accept the proposed move, okay? This proposal distribution can take on many different forms, okay? With the goal being to use the proposal distribution that efficiently explores the regions of the parameter space where p theta has most of its mass. So the proposal distribution can be different, okay? I mean, you can see in the discrete partition case, it's just like left and the right, right? I mean, and with 50-50% chance. I mean, that's so simple. But in a continuous high dimensional case, what do we do? Okay, we just need to make sure a proposal distribution for that we are going to use for proposal. I mean, it's going to have a quick way to generate random values. Okay, I mean, so pretty much like any distribution, any reasonable distribution, you know, it should be good enough. Okay, but for our purposes, okay, we can consider a generic case in which the proposal distribution is normal, centered at the current position. Okay, I mean, we know that a normal distribution or Gaussian distribution can be generalized to high dimensional, right? I show you guys like the two-dimensional Gaussian, right? Okay, and for n-dimensional Gaussian, it's pretty much just straightforward extension of like the second dimension, the two-dimensional Gaussian. Okay, so it's, I mean, we know that Gaussian distribution is simple, it's easy to draw, you know, random value from. Okay, so I'm not saying you have to use Gaussian distribution for the proposal distribution. I'm not saying that. I'm saying it's a easy, it's a good candidate. Okay, it's just a good candidate. Okay, so the rest, okay, talks about like that you know, using like a Bernoulli likelihood and beta prior. I mean, for like the you know, the coin flips. Okay, because you can use that to use coin flip to justify the generalized match-Paris algorithm. But you know, I will skip that. Okay, this set of slides, okay, because as I said, this set of slides comes from the Doing Bayesian Data Analysis book. Okay, so some of them are useful, but some of them I think like we already talked about, so I will skip that. Okay, so this so okay, but this slide is important. So representative parameter values can be this is the why match-Paris algorithm is so important. It's, I mean, why it is you know, it is designed. I mean, it's considered like a very, very good. Okay, so representative parameter values can be randomly sampled from complicated posterior distributions without solving the integral in base rule. Okay, remember like the denominator, the p of d, okay, is the term that we need like to do the integral, and that's the difficult part. Okay, that's the difficult part. I mean, when it comes to like analytical like a solution. Okay, if you want to get a closed form of the posterior distribution, I mean, a lot of time you will end up like you know, having trouble with like that p of theta, p of d, okay, p of d. Okay, so by using only simple proposal distribution for which efficient random number generators already exist. Okay, so we don't need to use that. I mean, we don't need to do the integral. Okay, instead we just use a proposal distribution to explore the space and to use like the p move. Okay, to determine like whether or not to move to that place. Okay, by doing so, like eventually you are going to generate like samples that that can be used to describe the posterior distribution. The more important thing is, okay, always need to decide whether to accept a proposed parameter value is the mathematical formulas for the likelihood function and the prior distribution. And these formulas can be directly evaluated from their definitions. Okay, so those things are easily evaluated. Okay, so you may wonder like how. So yeah, this is a sampling process. So why is sampling more effective than the grid approach? Okay, you say grid approach, we just find the value, okay, at the grid points, and then you approximate the posterior by finding those values, and the integral will become like adding all those values and use that as denominator. Okay, so it doesn't look like it's going to be an issue. Okay, and it looks like a grid approach. Looks like it's also efficient. So why sampling technique is more efficient? It is because, okay, in the sampling, this metropolis sampling process, you can see that it's going to jump. It's going to jump to the places with a higher p theta value, right? It tends to jump to those places with higher p theta values because of the p move, how the p move probability is calculated, right? Okay, if that place has a higher p theta value, it's more likely we accept that proposal, right? So it means that, okay, we are going to naturally stay at the places where the probability mass is larger. We will naturally stay at those in those areas. But for the grid approach, we treat each point with the equal probability, right? Each grid point has the same we just treat them the same, right? So if you use the grid approach, you will find which is most. Actually, it's always the case. I can probably say that. Okay, like a lot of distribution only has values at some location in the distribution in the parameter space. Okay, very small location, only a very small region. That distribution has value, and in all the other parameter space. Okay, even though in the high dimensional parameter space, the parameter space can be very, very huge, right? But in maybe 99% or even higher than that, okay, percentage of the distribution, the parameter space, okay, that you pretty much always get like some value very, very close to zero. Okay, so using a grid approach in such a case really doesn't help. you are going to just waste your time, okay, if you use grid approach, because you should just treat those places, you just, because if those areas is has a zero value, you don't even need to bother sampling at those in those areas, right? Okay, so, but if you use grid approach, yeah, I mean, you are going to end up like calculating value from those areas. Okay, but if you use this type of random walk approach, yeah, its mechanism, automatically, forbidden you to move to those areas. Okay, because if the p theta is close to 0, you just don't go there. It's impossible for the proposal to be accepted, right? Okay, because the proposal distribution, how the proposal distribution is determined to be accepted or not. Okay, how we decide it is accepted. Well, we will naturally, okay, the random walk will naturally, sample more in the area that we have higher value in p theta. And it will naturally stay, almost, it will naturally spend almost no time in the area where the p theta is close to 0. Okay, so this is very, very important. Okay. So yeah, I mean, there are other sampling techniques. That book talked about Gibbs sampling, but I think just like in our book, we use another sampling technique. These are all like a variation of the Metropolis algorithm. Okay, so I will skip this because I think like these are not the target. Okay, I mean, there are so many sampling techniques out there nowadays. Okay, after the Metropolis algorithm was proposed, okay, this like 20, 30 years, I mean, has the Bayesian data analysis field, because it has become so popular. Like a lot of mathematicians and the statisticians spend time developing like sampling techniques. Okay, but so I don't think we will we'll move to this one. Okay. So remember, like when you prepare your final exam, I'm not sure if this is this slide like in your PDF file. No? Okay, I'll update this. Okay, I mean, because I think like I cut like the previous PDF file short. Okay, so I didn't include this some of the rest of discussion. Okay, in the handout that I have the TA upload to the E class. So I will update the slide. I mean the handout. Okay, in the E class. But keep in mind, I will not cover everything in this set of slides, okay, in the final exam. I will only cover what I talked about in class, okay, in the final exam, okay? So any simulation that samples a lot of random values from a distribution is called Monte Carlo simulation. I told you guys Monte Carlo refers to the random process, right? Okay, so Metropolis algorithm and Gibbs sampling, all the sampling techniques are specific types of Monte Carlo process, okay? Because they involve, they are, in nature, a random process. Okay, the random walk is a random process. So any process in which each step has no memory for states before the current one is called a Markov process. Okay, and a succession of such steps is a Markov chain. Okay, because remember, like in the Mach-Paris algorithm, okay, you move. Okay, let me use the simple case of the Mach-Paris algorithm. You see, like the partition move, okay, to either the left side or right side of its island, right? Okay, so he does not move to all the island, okay, in the next step. He can only move to the nearby islands from the current island that he's located, right? Okay, so that's what I meant by, okay, each step has more memory for states before the current one. Okay, say if the partition initially at island 1, okay, after a couple of movements, he moved to island 4. The next step, he can only move to island 3, island 5, or stay at island 4, right? Okay? And it has nothing to do with whether or not few steps earlier he was at island 1. It has nothing to do with that, right? Okay, the only thing that is going to affect his next move is the location, the current location of this partition, right? Okay, so that's what I meant by it's a Markov process. Okay, only each step is only affected by the previous one. That's it. Okay, not the like 2 steps before or something like that. Okay, so a succession of such steps, or like the whole random walk, okay, can be considered as a Markov chain. Okay. So there are 3 main goals in generating mcmc sample from posterior. Okay. First, the values in the chain must be representative of the posterior distribution. Okay. So they should not be undoubtedly influenced by the arbitrary initial value of the chain. Okay. And they should fully explore the range of the posterior distribution without getting stuck. So this has 2 important meaning. The first one is the initial location should not have impact to the result. Okay, if the initial location has impact to the result, that means your chain is not representative enough to the posterior distribution. Okay, and also, okay, your chain, okay, should fully explore the range of the posterior distribution. In other words, the proposal distribution needs to be able to, explore the whole posterior region where the p theta has non-zero value. Okay, so obviously this has something to do with how effective is your sampling technique. Okay, so different sampling technique. For example, like in this book, I mean, the Mach-Paris algorithm, the Gibbs sampling is much more effective. Of course, different sampling techniques, I mean, has also different assumptions, okay? I don't expect you guys to understand all the sampling techniques in detail. That's just impossible, okay? I mean, but I expect you guys to understand, for example, like the basic the idea of sampling technique, at least like the Metropolis algorithm. You need to understand how it is like, you know,